They understand. Stupid guy.
Sign this. Part, yeah, still working. Sign this too.
Yes, sir.
If anybody didn't sign, would you mind signing this list?
Everything go well?
Yeah, it's good. Except I said, way too many times. You got another pen? I love it that you
We handed out a bunch of questions, asking for feedback, and all the pens we gave out didn't work.
didn't get much feedback, right?
Yeah. It worked.
You gonna switch our board up?
I'm about to.
Perfect, thank you. We got a QR code. Just stick up there. So.
Sorry for going over.
You're not over. You're good.
So last year I was here, the guy went over 35 minutes.
35 minutes.
Yeah, I think.
That's what I told the moderator here. So I told my Chris, I said, tell me if I'm going over.
Don't know yet.
I don't know. I might be.
We're able to monitor, have.
I'm gonna get a copy of this or should I take a picture of it? I don't know. I think I do, but.
Yeah, but you want to, did you? Go ahead.
Here, I'm gonna start on time because I hope I don't talk over. My name is Sherri Roberts. I'm manager of larger placements for players, aftermarket team at Zink in Tulsa, Oklahoma. I'm honored to be here with you guys. I'm gonna talk a little bit about steam flares and how some technology we have can help improve efficiency on steam flares and help you meet some of these regulations that have come down the pipeline in the last few years. Just a little bit of brief history about Zink. We get a lot of questions lately. Are you guys Coke? Are you guys Zink? Who are you? We are still Zink. We're still very proud of our name. But we are part of a company called Coke Engineered Solutions. We found some synergies across our sister companies. Some of them you may recognize up here. So we kind of teamed up with a lot of them, how we can bring value to our customers, how we can team up and bring those options to you. And that's why we have the umbrella company called Coke Engineered Solutions. So if you hear that name, we are still Zink, very much so. This is just kind of a program we have with our sister companies to help bring value where we can. Those are slides. I just don't want to go over on time here. So I think most of you were probably in the training yesterday that our Spectrum friends gave, and it was a great update on regulations. So I'm not going to spend a lot of time on this, but the main point of my presentation is how we're going to address these regulations for you guys. So just quickly, all of you, I'm sure are familiar with the EPA emissions updates that have come out. Stricter requirements for flares, stricter requirements, especially on steam assisted flares. So from all this testing, it was found that even when 40 CFR 60.18 is met, flares can be oversteamed. Their combustion efficiency can be greatly reduced. So this is the solution here that we're trying to find is how can we meet this? How can we help you guys meet these needs? This is the TCEQ flare testing that was completed at the Zink testing facility. Most of you have probably seen this slide, but I like to show it just so you can see how the testing was completed. The flare was at grade level here. This is what I like to call the sniffer. So it's basically taking downstream of the plume of the flare, trying to catch all of the stuff coming from the flare, and then it was taken through to a trailer that was then tested and seen what was actually coming out of the flare, so that destruction efficiencies and combustion efficiencies could be found and truly flared. It's really hard to do this at a large case, like in you guys' facilities on a staff, which is why our test facility was used for it. While it was done at the Zink test facility, We did not run the test. It was totally independent. We just basically provided the facilities for that testing to be completed independently. Here are some of the results from that test, but also the marathon consent decrease. The y-axis here is combustion efficiency, and the x-axis is the combustion zone net heat value. I'm sure most of us have heard that statement, heard it used, but basically it's the mixture of your flare gas that's leaving your flare tip and included any steam that's added into that system to bring that heating value down. So you have to include that, what I like to call the soup mixture. You can see as that reaches that 200 to 300 combustion zone net heat value, how quickly those combustion efficiencies drop off. It just takes a nosedive as soon as you hit it. And so that correlation was found from going through all these test results, and that's where the combustion zone net heating value values came from and put into those regulations. I really like this slide. We got it from the TCEQ. They've actually used this in quite a few testing, but we borrowed it from them. And it was also shown yesterday as well too, but I want to hit on it again. The key part in all three of these pictures is that the flare gas is exiting at the same flow is going to the flare at all these times. It's the same mean value in all these pictures. The only difference is the steam rates going to the flares. You can see the differences in how these flames look. I would argue even in this one, there's not a lot of old flame going on. But what you want to look at here is the steam to vent gas ratios. And this first picture, we have a very bright flame, getting pretty good destruction efficiency just by visually looking at it. But even it was proven it's a 99.2 destruction efficiency in that first picture. Your steam to vent gas ratio is 0.29. That's a very low steam to vent gas ratio. Most flares out there don't operate that low, and steam flares do not. But let's jump it up just a little bit. Okay, 0.29 to 0.54. That's just like a little bitty tick on your steam valve, right? You can kind of control that close anyways. Not very good. But we jump it up to 0.54. Your destruction efficiency automatically drops to 90.6. That doesn't sound like a lot, right? Not too much. That is significantly a lot for emissions coming out of your flare. So you're at 160 pounds of unburned flare gas. Now you're at 1,880 pounds of unburned flare gas. So that's a lot more flare gas that's emitting from your flare. And this last picture, you don't really see a lot of flame at all. We've only bumped that steam to vent gas ratio. We started at 0.29. We've dumped it to 1.05. Once again, not very much of an increase in your steam. It's really hard to fine tune a steam control valve at that rate. But your destruction efficiencies dropped all the way down to 27%. Okay. That's 14,540 pounds of unburned flare gas leaving your flare tip out of 20,000 pounds an hour. I'm sure nobody wants that coming from their flare, let alone the EPA, right? So this is the significance of turned down flare operation. Sure, at high flows, flares are much easier to control. It's easy to get those steam to vent gas ratios. When you're at turn down conditions, it's very hard to fine tune your flare control. So what did all this testing tell us? I like the joke I was told yesterday, water puts out fire, right? That's essentially what we learned in all this testing. If you oversteam a flare at turn down conditions, you reduce your combustion efficiency. From this testing, it was found that if you have luminous flame up on your flare tip, it's a pretty good assumption that you're having good destruction efficiency coming out of that flare tip. Operating at the incipient smoke point can be shown to have the highest destruction efficiency. You guys know what I mean by the incipient smoke point? Getting a couple yeses. That's literally right before it starts to smoke. So you start to see those black formations in your flame, but it's not actually exiting. So that's what we consider an incipient smoke point. So your flare operating envelope is going to be much tighter than it is in the past. Okay? Used to, this is all we were worried about. We didn't want to see smoke coming from our flares. A lot of operators even wanted to see this, right? They didn't want to see any flame coming from a flare. Of course, we all know that that's not a very efficient flare at all. But one of our long-term process engineers actually retired last year. He likes to tell a story. We got a call having a complaint of odor coming from a flare. So he goes out there trying to help him out, and this is what he sees. So he says, well, guys, you're putting out your flare, you're putting way too much steam up there. You need to back it off. They did. Flame came up, odor went away. They said, hey, this is great, let's go to lunch. Before they even leave the refinery, the head of the refinery calls and said, what'd you do to the flare? Why is there a fire up there? You need to turn that back off now. It's like, well, that's what we had to do to get rid of the odor. I don't care, I don't want to see a flame up there. This is what we get complaints about, this is what I get calls about. I get calls about this in the middle of the night. I don't want a flame up there. So it's just a knowledge thing. People don't understand it. People don't understand flares. Just like we were talking about yesterday afternoon in California, getting 911 calls when there's a flaring event in California. This is what we want to see. So it's going to take knowledge and explaining this to everybody, but this is how your flare should look. And you want that preferred flame, luminous flame. So we had the refinery rules come out, so everybody's familiar with those. They've already been implemented. The biggest thing that came from there is that net heat value combustion zone. So at high flow rates, sure, no problem. These steam flares are no problem at all. Where we struggle with this is that turnout conditions, okay? All steam flares should have a minimum flow going to them, steam flow going to them at all time to help protect them. If you don't have that minimum steam flow going, there's a good chance you're gonna burn up your flare very quickly. So there's a trade-off there. Do I want to not have to add a gas to my flare, or do I want to protect it and not have to replace it in 6 months? All flares should have some sort of minimum steam going to it to help protect it over time. Some other benefits you got out of it is that 12 heat value for hydrogen, so that's a good thing. You got hydrogen, and that is based on a 15-minute walk average. So just a quick glance of what you used to have in your refinery ground flare, and this is what you need from the refinery rules. You have to have a minimization plan. You have to measure your flare gas. You have to be able to give the compensation or the LHD measurement of it. You have to have an assist gas control. If you're not meeting that net heat value combustion zone, you have to add assist gas to it. You have to be able to measure your assist steam or assist air, depending on the type of flare you have. And also you have to be able to monitor with a camera and keep that in your files. So I just like to show that to show the big difference between flares. When I first started in the flare industry, we didn't have any of this, so it's very nice to know. Ethylene rules came out, very similar. Really the only additions that added to it was some topics on pressures. So what does this mean for flares, right? We want to be able to minimize your flare. They're wanting you to minimize your flare gas flow as much as possible. They don't want you to flare. But that means that it's much harder to operate in turnout conditions, and also have to minimize your steam flow if you're not already after minimum steam flow. That increases your net heat value combustion zone. If you don't have enough, you have to add assist gas. All of these kind of factors have to go together and get very complicated on how to operate your flare. And this operator is not worried about the flare. He's worried about these 100 other things that going on to your flare system, right? So let's think about steam flares. How many of you have steam flares? Yay, good. I have some steam flare people out there. Just a little bit of history on the flaring industry and flaring world. The flaring world was started in about 1940. Okay, that's when the government started regulating venting. Steam flares were not part of that at that time. Basically, it was just a fire up on a stick. Okay, they called John Zink and said, "Can you give us a burner on a stick?" And that's what we supplied. That started the flaring industry. But around 1950s, they started getting some more complaints. We've got this rolling black smokestack coming across our sky. People don't want to see that either. So how do we make these flares smokeless? That's when steam flare technology came into the world. Around 1950, upper steam injection flares only were developed. Didn't quite look like this, was a little bit more elementary, but this is a very common upper steam flare that you might see out there today. There's still a bunch of people out there. There's nothing wrong with these flares. They still work in a lot of applications very well. The problem with them, our flames get larger and larger. These get larger, and literally that upper steam alone is not enough to inject into the middle of your flare gas plume and really treat it where you need to treat it inside of that plume. So that's where this style of flare came into. We like to call this the SA style flare, which stands for steam and air tube. So you have not only your upper steam injection up here, but you have a lower steam injection as well. So you have steam and air getting pulled in, pushed through these tubes, and up right into the middle of that flare gas, exiting your flare tip and really treating it where you need to be treated to get that smokeless flow, higher smokeless capacities. These flare tips can go up to very large in size. You know, there's 72-inch flares out there, 84-inch flares, some even bigger. There's one over in Singapore that's massive, has a huge smokeless capacity. So both of these are still great technologies. There's a whole bunch of them everywhere. Around 25 years ago, John Zink thought to ourselves, like, how can we be innovative? What's the next solution that's going to come to the steam flare world? What do our customers need to really take this to the next level? And the XP was developed. This is called the Steamizer XP flare system. It's been on the market now for around 15 to 20 years, so quite a while. I think it looks like a spaceship. You can kind of see, we brought our model over there, a little bit funner to see in a 3D model version than just the picture. So, but there's no upper steam on this flare tip. There's no center steam. All the steam is injected at the lower portion only. So that is your steam manifold right there. There's a windscreen here, and the steam spiders are right there. That's how you inject the steam and air system. I didn't hit on this earlier, but what is this steam doing in this situation? Does anybody know, how does this steam make it smokeless?
Bringing in a large volume of air with turbulence.
You know, so it's not steam, but it's the air. Thank you. That's great. That takes it with it. So if I want air in there to make it smokeless, why wouldn't I just use an air flare? Anybody know that? Steam is actually much more efficient at entraining air than air is itself. Okay, so I could put air through the steam line at the same pressure, the same flow. It would not entrain near as much air as steam would itself, and that's because steam has a higher critical velocity, and that's why it's able to bring in that extra assist air. So that's why steam flares are much more efficient than air flares. And most of the time in your plants, you have some extra steam available, have a blower, so it's an available utility as well. It doesn't cost you a lot of money over supplying these huge blowers that you have to run on power and things like that also. So.
We have had questions like with the abnormal situations of the plant, like where they've lost their steam capacity or whatever. On all Black Star. And so we give them some guidance with the user. We tell them it's gonna stop the beast.
Yep, you can put air through steam lines in critical situations like that where you have outages. It's not gonna work as well, but at least you're gonna keep your clear.
Where does the gas come out of that bubble there?
Great question. Hard to tell in the spaceship funnel. So this is the actual flare gas inlet right here. So this would be attached to your stack. The gas is allowed to travel through here and throughout this entire head right here. And then they come up through the module sphere. These straight steam tubes stuff in the middle, and they mix all here as they exit.
So I guess there's a tube inside of that tube?
It's in the zone.
Yeah.
Makes the top up here. So why is the XP so much better than other flare tubes? Than those other ones we saw, right? So it provides superior smokeless performance through what we call moderated shear mixing. That was what was in the patent that we filed on EXP. Basically, when you burn hydrocarbons and reduce air mixtures, carbon particles are able to form, which build upon each other and create soot particles, which is then smoke. Okay, so this is especially important for unsaturated hydrocarbons, which we like to call soot precursors. These are like your olefins and propylenes of the world. And they're just very reactive. So as soon as they start to heat up, they start to crack. They start to find those carbon particles to attach to. There's not oxygen there where you need it. And that's why the XP can provide superior performance over those other styles of flare tips. Kind of like in your ethylene furnaces, you get coke filled up in the tubes. That's all carbon. So that's what your flares do as well. If you don't get that oxygen there for it to react with. So the moderated shear mixing is up here at top. Okay. So that's a key part of the XP. The other part is secondary air entrainment. Okay. So you have this flare tip. If it was a 48-inch body on those other styles of flare tips, you have this huge bluff body that you're trying to pull ambient air around in it, trying to increase that mixing energy around it. But around this big bluff body, you just can't get as much mixing. You can't pull as much ambient air into it. We've broken this up here into different arms, smaller body, breaking it up in little ones, and you get more perimeter area that you can really pull that ambient air outside. And so it creates its own jet as it's exiting here at the top and pulls in that ambient air also to help provide that additional smokeless capacity. Here's a better view with the windshield off the bottom here. You know, the steam jets here going into a straight tube. Goes up inside that tube as well. So what's that look like in steam to vent gas ratios? So you have your steam to hydrocarbon ratios here on your y-axis. You have your smokeless gas flow here on your x-axis. The blue line here is that standard SA style flare tip that have the upper and lower steam rate. The XP here is the purple line. So not only across the board are we just better on steam to hydrocarbon ratios, but also look at the additional smokeless gas flow you can get over an SA style flare tip. The red line on there is the API's recommended steam to hydrocarbon ratio for propylene. I like to show this because I get called a lot and say, hey, my flare is not meeting the steam to hydrocarbon ratio out of API. How come? Especially at turn down conditions. So first of all, the API is just a set steam to hydrocarbon ratio across the board. It's hard for your flares to meet that at turn down conditions. Just because steam flares are not as efficient at turn down conditions. You have this large steam jet that's designed to flow thousands of pounds an hour, but at turn down, you're flowing hundreds of pounds an hour at a much lower pressure. So it's not near as efficient in those situations, which means that your steam to hydrocarbon ratios automatically go up in those conditions. I didn't check the volume on this, so it doesn't blow us out. But this video is on our website. If anybody wants to go take a look at it at any time, it's just an overview of the Steamizer XP. I like to just show the 3D model here. It's kind of fun to look at, so. Gonna zoom in up top here, see the different points as we go through it. The first is gonna show you here the pilots. Not every module is piloted because they do cross lights. So that's why you don't see a pilot on every module. Zoom in here where all the steam is coming in on the lower portion of the flare tip. Steam header. Then you have your straight steam tubes. That's another big thing between the SI style flare tip. On the SI style flare tip, you have vent steam tubes. You have to overcome that back pressure through those steam tubes to pull that air in. On the straight steam tubes, we don't fight that issue. So you have less pressure drop you have to overcome, which allows you to pull in more air and be more efficient in those situations as well. I forgot to mention that earlier. So just some benefits that the steamizer can offer as well too. I think I just talked about that point, but here's another view of it. So you can remember what it looks like. You have the vent steam tubes here. That is that additional pressure drop I was talking about. You have to overcome to really pull in the air to get that steam and air mixture up here up top. We don't have that on the XP because they're straight steam tubes. The other part with this style of flare tip is it can be difficult to control. Okay, you have the upper steam line you have to control, you have the lower steam line that you have to control, and a lot of times on those flare tips, you also have the center steam line that you have to control. So how do you operate these flare tips? You need to increase that lower steam to around 70% capacity before you increase the upper steam very much at all. From that point on, you can pretty much go up linearly and control, providing as much steam as you can to that flare tip for smokeless flips. But why? Why can't I put my upper steam where I put my lower steam on? Anybody ever seen this phenomenon? Know what it's called? Capping. I got a nod head over here too. So basically the flare gases are caps. That means we cap the flare and it pushes flames back down the tube. We took a video of this at our test center to kind of see it in action. So we've got a smoking flare here. Somebody switched the valves and turn around, we don't know. Put the upper steam on first, maybe just an operator turned the wrong tube. You can see how much damage that could quickly damage your flare tip. I've also taken them, I didn't take it. Somebody else took the muffler off this flare tip. So you can really see what's happening here. But if that muffler was there, you're damaging your refractory in there, you're damaging the muffler itself, you're damaging your mixers, your pilot mixers are down here, and also the steam jets and stuff down there. If flares operate like that for very long at all, can very quickly damage your flare tip. We've seen flare tips have to be repaired in less than an hour for operating in this type of situation. So not something we want to see, not a good situation to be. Unfortunately, it's just part of operating these flare tips that can be difficult to do, especially with an operator that's got 100 other things going on. He's not really worried about the flare. So some videos of the XP. There's one now. Burning propane. What I really want to point you out to here is steam saving compared to the SA style flare tip. You can get around 31% steam saving burning propane. The XP versus the HSA. Next video is propylene. Look how much brighter this flare is. So that's one of those unsaturated hydrocarbons I was talking about. You can see those black formations already happening here. Those are those carbon particles that are starting to form very quickly down here low in the flame. But with the XP, we're able to treat it in time so it doesn't exit the flare. And this system has 36% steam savings. I must have muted this video, but not the other one. So it's much brighter, more luminous flame on the propane. So you can see those differences in the type of flames and how they burn on different applications. I've got a few case studies here I'm going to go through pretty quickly. This first one is actually the first 2 XPs that we ever supplied. So this is to a Europe refinery, and they are actually twin stacks. You can see them here. There are 2 XPs that are installed in them. They came to us, not just us, they came to multiple flare vendors, but the situation that they were having, they needed higher smokeless performance, but they couldn't provide any more steam to the system. They wanted to actually reduce how much steam they were even sending to the flare. They were having issues with flame stability on their current system, which is causing them some noise issues as well. So they selected the XP, took a gamble on us. This was the first one that we've ever sold. I'm very happy with it. This flare's been in service now close to 20 years, and they've never had to replace it. Actually, we've never had to replace an XP at all due to damage. We had one that they burned over in the Middle East for about 6 months without steam they had replaced, but not much you can do in those situations. So But it met all their needs. They were able to reduce their, or increase their smokeless performance, reduce their steam usage, get rid of the noise problems, and have great flame stability on these flares. Very similar, this one is in Korea, Hanwha Total Petrochemicals, used to be Samsung, but they changed their name on us. But same, a lot of very similar situations. This is actually a 60-inch XP. I think this is one of the first 60 inches that we sold in the XP style system, but had the same issues, smoke capacity, noise issues, stability, and they were getting a lot of noise complaints. After extensive evaluation, not just John Zink, but other flare vendors as well, they selected the XP, installed it there, you can see on the system, very large flare tip. Since startup, they were able to see an increase in smokeless capacity using the same steam as their tip, and they also got rid of their noise and stability issues. This plant actually took our old SA style flare tip down and set it up in their facility as like a monument of how well the flare had served them, and we're happy with it, and even happy with the new system. So different cultures, it's really neat to see. I'd like to go see it sometime. So this is my favorite one. The plant previously that I talked about is in, pretty much a complex that has several plants in it, like many of us know, like around here. Based on the success of the startup of that XP, several of the plants in the area called us and said, we want that same flare tip. We've seen how much improved performance they've gotten out of that flare tip. We want the same one. So we've actually sold several more in that same area based off the success they saw from the old flare tip. So this is my favorite case study. Last one I'm going to share with you, this is a Gulf Coast olefins plant. It's a little bit closer to home. They called us in 2013 and said they had the New Year's resolution to give up smoking. We're like, that's great. Not sure how we can help you, but be healthy. We love that. But they weren't talking about that. They were talking about their flares. They wanted to cut out the smoking from their flares. So to show you what it looked like, this is their old flare tip. And this is their new flare tip operating about the same flow rate. And those are the differences that we provide with the XP from the old style SA flare tip. So talked about all the benefits of the XP. Low steam consumption, they're easy to operate, all steam comes from the lower portion only. They have proven operation and long tip life. These have been in the industry for a while now. There's no upper steam manifold in that flame zone. You have to worry about getting damaged. You can't cap the flare tip. And we also put body thermocouples in these XPs as well, so you can watch for internal burning and react to it versus most flare tips don't have that. So that's another way we're able to simulate these flare tips. But what I'm really here to talk to you about, I'm just talking about this. 256, we're doing good. So in the past, as flare vendors, we were always worried about your max hydraulic capacity. We wanted to know what you wanted the flare size for, how much smokeless capacity can we give you, what's the best that we can do in those situations. So we were worried about that upper end of your flare capacity. What we really were even thinking about was those turnout conditions. Okay, nobody worried about turnout conditions. They just wanted to know the max smokeless capacity you could get out of the flare tip. And so this has been a neglected design philosophy. Most of these flares live their life at very small flow rates going through the flare tip. So this is something that's important to you guys. Something we probably should have thought about a long time ago. The regulations really brought it up in detail. We need to think about these turn-down conditions and how we can help in those situations. Really help meet that net heat value question zone. So this is actually something that we use for flare gas recovery, but I like it because it shows flare flow profile across a long time. I think this is over a year's situation here. Where is this flare living at all the time? Where's the flow rates? Way down here, right? So here's your max capacity of your flare, but this is where your flare is performing most of the time. Really, those turnout conditions, we'll zoom in a little bit even more on that. So this is what we need to be worried about. This is the next situation in flares where we're really talking about the industry. So when all the refinery regulations were coming out, we once again innovated, trying to think for ourselves, what can we do? How can we help our customers meet this need? And that's where we developed the stage steam. So we want to be able to meet that combustion zone net heating value. We have to meet that dilution effect for minimum steam. So you aren't having to add a sysgas to your flares. So if you don't meet that net heating value combustion zone, you're putting money into your flare and emissions. So if you're adding that sysgas, you've got more emissions coming from your flares, and you're paying for that sysgas going out of it as well. Not anything that anybody wants to do. So we had a patented product called the XP stage system come out. It provides extremely low steam consumption at turned out conditions, with still protecting your flare tip and also providing some small smokeless flow rates as well. So what does that mean? normal steam flares, you have a large steam jet that's designed to burn, let's say that one of these steam jets is designed to burn around 13,000 pounds an hour coming out of it. When you turn that down to the turn down conditions, you've got 333 pounds an hour coming out of it. Does anybody know what pressure you'd be coming out of the steam level at? It's designed for 100 psi at max. So when you're down to 300, what do you think you're running at? Take a guess. About 1 psi or less. So it's not very efficient coming out of an orifice, right? All of our steam jets have orifices drilled into it. Turn down conditions, you're at 1 psi. It's not coming out of there very fast. And the wind is just gonna kind of blow away. It's not really pulling any air there to protect your flare tip at all. Really, what's happening there is more you're just protecting your steam manifold by cooling it off. Okay, got a overflow going through it. So we developed a second steam manifold that's installed in the same place, but they're designed to operate at those low flow conditions. So you have the low flow conditions, but it's designed to operate at that high pressure. So you can take advantage of that high pressure and really pull in those air in those low flow conditions. So you're pulling in the air that you need to actually get some smokeless capacity, actually help shape your flame a little bit, but it's requiring much less steam to do that situation. So then you don't need as much minimum steam to the flow, which can help you meet that net heating value questions. Steam control is still simple though. Even though you might have multiple steam lines going up to your flare tip, up to 2, maybe 3, versus just 1, it's all coming at the lower portion of your flare tip. You still can't have the flare tip. You just put it all in parallel and you're seeing signal. Operators still just have one steam control system they have to control. So it's still very simple in that fact. So I pulled the same graph earlier that I showed you. I added a new line here. So just a reminder, the blue line is the SA style flare tip. The green line here is the XP flare tip. And then I added an orange line. My favorite color. Does anybody know why? Oklahoma State Cowboys. Okay, go Folks. Not any other orange that some of you guys back there might like. Yeah. So, but what I really want you to look at on this graph is the turn down conditions. Okay, you still have your same maximum smokeless flow, but at these turn down conditions, look at how much improved your steam to hydrocarbon ratios are. And that's really where flares operate all the time. That's where these huge savings can come in. So you don't have to add a syscap to your flare tip. And you're still able to also offer some increased smokeless performance over normal steam flows going through normal steam manifold. What's it look like? Let's take a zoomed in look here. We also do have an 3D model. I know that will kind of be in between, but I'm gonna keep this up for the end of the day. If anybody wants to come up and look at it, also be out here too as well if you guys want to come look at it. But here's the whole XP in our shop, zoomed in. This is the stage steam manifold here around the outside. This center jet is the main steam jet. So that's kind of the difference that you see there as well. So they are different steam manifolds. They do have to be controlled separately. It's still very simple to operate. So we talked about net heating value combustion zone, how that's going to help you smokeless, right? What everybody wants to talk about in today's world is the carbon footprint. Okay, how can this help me in the carbon footprint world? So we did a little calculations using the EPA calculator out there on carbon CO2 emissions, I should say. And so an SA style flare tip at the same size, which has the vent steam tubes, would have a minimum cooling rate of around 1,200 pounds an hour. With the stage steam system on the XP, we can get that minimum rate down to 600 pounds an hour while still protecting your flare tip, still providing that performance you need. And that's going to be a natural gas cost savings to not meet that net heat value combustion zone of around almost $22,000 a year. Now this is using this number. This was done a while ago. That number could have changed now and then. But the big thing I wanted you to see is the CO2 emission savings. So 232. So that's a huge savings there factor on your CO2 footprint as well that you can use and to look at. We know everybody's trying to look at that carbon footprint savings and how you can help that. So it's just another example I'm going to show there in a different view. Concluding discussions. Okay, the XP's been out there for 15 to 20 years. You know, there's been over 100 of them sold in operation as well. But I've still got 15 years on here. We're nearing 20 now, and you know this as well too. So, like I said earlier, none of them have been replaced in that time, unless they were just really operated without steam for a long time. We actually even had some go through that freeze down here in Texas that you guys had 2 years ago, maybe. Operated without steam for several days, but they were fine. There was no damage to them. They were able to start back up, no issues at all in the situation. So they seem to be very hardy. Is that the right word I'm looking for? That's really good. Robust. That's a good word. So very robust, can last in those situations as well. So just a great flare tip overall, and then adding that stage speed to this can really take it above that next notch. So it's the only flare tip on the market to offer these turn down steam optimization. It is patented, so John Zink is the only one that offers this type of this system. And all of this was still offering high performance. Anybody have questions? I do have a QR code up here.
I'm just seeing with the newer styles, stage scheme, what's like the cost differential with like a normal FSP?
Sorry, move right.
Yeah, I'm just thinking like to add all that extra steam piping and all that, what's like, I don't know, you're not gonna be dark, like is there a percentage increase in price?
I don't know total installed cost. Me on the aftermarket side, usually I'm replacing an SA, so those steam lines already exist. So in the past, when we put an XB up there, we weren't using the steam lines at all. Now we can reuse them for the stage steam system. But adding, Chris, what do you think on the standpoint of? Because it's a very small team, like this is like a 2-inch line, yeah. Not very difficult, so.
Very nice and punished. As opposed to the including. Did you burn in the flames?
Great question. Wish I had a more version number there. Sorry. But I do have a QR code up here. If you guys want to take a picture of it, it takes you to some of our brochures, some of our information as well. And just a little plug also, we do have our John Zink Process Flares course coming up. It will be on April 26th to 28th. That is in Tulsa, Oklahoma. We do full on training across all topics of flares, pilots, steam flares, air flares, how to design a flare, operation and maintenance, all the above. Would love for anybody to join us. If you're more interested in that, let us know. That QR code will take you to some information on that as well. And I have brochures up there also, if you just want a handheld brochure also. So, but I appreciate you guys coming. Like I said, I'm gonna leave this up to the end of the day before I take it back down. So if you have any questions, I'd love to answer them as well. I might even have a little bit of time for the next presentation if you want to come look at it now. So I finished on time. Yeah. Thank you guys.
Thank you.
I'll let him take the recording off. I don't know how to do that. No, I know you guys were. I know. You picture with them yesterday. Yeah. Oh, did everybody sign in on the sign up too? Perfect. Thank you guys.
Yeah, I mean, I always do. That's me too.
Smart, right?
Yeah.
We have to have oh, darn. But I won't be here. We're gonna do tomorrow.
Okay. Hello. Yes. The fourth one. Oh, okay. Yes.
If you don't mind, I'm gonna jump on here. I'm actually gonna throw slides onto the computer.
I know I need to pull up, I uploaded my new one, so I don't know if you just look it up from there or what.
Okay, so all the gas exposed.
I probably don't keep more than started with all the answers.
You said you're coming in here next?
Yeah. My latest, is that nowadays? Yeah, need to upload it. Last minute changes.
Yes, sir.
It's crazy. They want to complete a presentation like 2 weeks before the conference.
Yeah,
You guys pay.
I wish I was that organized.
Yeah. It's like, if this was only going to be, I could do that. Or. Not.
Go right ahead, sir.
I'm usually this, that's, I think it's really, it's like the mind. I was not really fine. I read about it. Oh, yeah. That it happens every time. Yeah.
Oh, I was just updating the thing. So I was gonna go and delete, yeah, you can delete the other one from.
If I record this,
Session.
it's okay if not.
Yeah, sure.
Inside of the station, you know. Yeah,